What unseen things will be revealed in this episode? Well, today we explore unique research that could help to reduce side effects of brain cancer radiotherapy and at the same time increase its effectiveness. Our guest leads a promising clinical trial aimed at unlocking navigation of ion beam irradiation. Hi, my name is Martin, and I'm thrilled to welcome here in Unseen Talks Dr. Mária Martišíková, who is a group leader at the German Cancer Research Center in Heidelberg. Hello, Mária.
Hello, Martin.
And I'm also happy to have here my colleague, Jan Jakubek, the Chief Scientific Officer here at ADVACAM. Hello, Jan.
Hello.
Mária, as I mentioned, you are currently running a clinical study called InViMo at the Heidelberg Ion Beam Therapy Center and Heidelberg University Hospital. What patients are involved in the study?
So currently included are patients which have cancer of the skull base. So it's not just deep in the body, but it's in vicinity of very important organs.
Mm-hmm. Yes, the tumor is hidden inside the head.
Yes.
Where exactly the tumor is?
So here we can see it in red, and you can see that it's very close to the optical nerves and brainstem, eyes, so all very critical organs. And in this image, we can see a more detailed position in the head.
Could it be removed in a traditional surgical way?
So surgery is not suited because it's very difficult accessible. You can see that you can somehow damage the structures around. And also with normal photon radiotherapy, the standard radiotherapy, the results are not good. And therefore, the ion radiotherapy is used in those cases when it's possible.
Yeah, what are the biggest advantages in this case of the ion beam therapy?
So those are the particular physical properties of ions which stop at the end of the range. So one can steer the energy to stop directly in the tumor. And in addition, they deposit the highest energy at the end of the range, so the highest dose. And in this way, the tissue in front of the tumor can be spared also better.
Yes, more broadly speaking, irradiation with ion beams is already one of the most advanced methods how to treat head and neck tumors. But still, you and your team are trying to improve these methods. Why? What are you trying to achieve?
So actually, the delivery of the radiotherapy is very precise, but the challenge comes from the patient because, of course, patient inside can change and the radiotherapy takes several weeks for almost every day, and we cannot see in the patient whether, for example, there is a tumor shrinkage or some swelling, and the only way to uncover it would be to take daily CTs, but this cannot be justified, so the dose would be too high for the patient, and therefore we need a method to see inside of the head without any radiation dose.
So the tumor itself, during the therapy, which takes several weeks, can move, shrink, or there are some new matters in the head, like
exactly.
mucus, for example.
Yes.
And this can change the effect of the irradiation. And the result is that the beam is not aiming directly into the tumor, right?
Exactly.
And what does it cause?
So it can be on one side that the dose in the tumor it's not sufficient, so there can be recurrence of the tumor. Or another way, when the beam is overshooting the tumor, we can damage exactly the sensitive tissues or organs which are behind the tumor.
Yeah. And therefore, at the current phase, the particle beams don't only target the tumor itself, but also affect a small portion of surrounding healthy tissue. You call it safety margins. Is this problem? These safety margins?
Yes, so first of all, the safety margin is used in all kinds of radiotherapies. And here it's very challenging because the dose is deposited very precisely, much more precise than in normal photon radiotherapy. And therefore, we have to be very sure that the dose is there where it should be and is not there where it shouldn't be. So therefore, we irradiate a small portion of tissue around, yes, so you can imagine it that the orange is the tumor and the peel represents the margin. And as you can see, when you peel such an orange, it can be easy that the peel has the same volume as the tumor. So it is, of course, of big interest to reduce this margin and in this way improve the radiotherapy.
All right, to sum it up, so you tried to make the ion beam radiotherapy more precise, more gentle, and this led to development of a new device. I will bring it. This is, of course, just a model of device called BeamTraX, which was developed together with ADVACAM. Jan, please, could you explain us, using the model, what exactly it does?
Actually, what you can see here, this is a set of detectors, actually, which can monitor what is going on during the therapy. The beam of ions is delivered actually through those structures here to the position of the tumor, and actually those ions would stop there. So we don't see them coming out of the patient, so we cannot use them for monitoring. But what is able to leave the volume of the patient head is secondary radiation, which is produced by those ions when they are penetrating into the head. So there are some small particles which are basically recoiled or emitted during these interactions, and those could be seen or detected by our detectors here. And these detectors would record the tracks, and those tracks can be back projected to the place where they are created. So actually we can reconstruct, in fact, path of the beam through the head of the patient. This recorded shape can be checked to the reference measurement where we are sure that everything is okay. And if there would be some difference, we can say, okay, the only thing that could change is not the beam, not the detector, but the patient. Something has changed in the patient, and then we should stop or people who are operating it should stop the procedure and make a new plan of irradiation of that patient.
And you are using the original of this model, of this device, in the clinical trials.
Yes.
What's the setup?
So it is the patient is first position of on the couch normally as for standard procedure, and then we bring the device. It's anchored then in the floor of the facility, and when everybody leaves the irradiation room, then we start the measurement from outside, and the patient is irradiated as normally for his therapy.
Jan, what is actually inside the box?
Inside of that box are 28 of our detectors. They are organized in 7 units, 7 modules, and each of those modules consists of 2 planes of detectors. So we have 2 planes, and whenever there is a particle going through, each plane records its position for each individual particle. And having 2 points, actually, intersections of this particle with the planes of detectors, we can back project, or to reconstruct the original path of the particle, and we can see from which point it was emitted, and it should be at intersection of the beam and the patient body. So if the patient body would be shifted, they would not come to that point, and we would see it.
Is it necessary to use the time pixels for this purposes, Mária?
So TimePix is a very versatile device. This is one of the benefits, and the second is that it could be customized in the way that it can be really used in clinics, which is very important, because otherwise such highly sensitive detectors with that area normally comes with a lot of cables and computers, and now it is everything here very nicely in the device.
All right, I will just remove it again. And we can try to explain it once more using this beautiful animation. Maria, what's happening here?
So first we saw the treatment beam, which then stops somewhere in the patient, and then here is the structure, which is inside of the device. As Jan said, the two measured points build the path of the ion, and we can look back where it is coming from, the secondary particles.
Does the device affect the therapy itself, or it's just sort of new eyes looking at the therapy?
Yes, exactly. So technically, it doesn't influence the therapy in any way, but we still have to consider clinics, and there we work a lot on the whole workflow. So it means that the patient irradiation doesn't take more than 5 minutes in addition, even less, which is used for positioning of the detector and then bringing it back to the not measuring position.
Jan, in the introduction, I referred to the system as a navigation for ion beam irradiation. In what sense it does serve as navigation?
Actually, I would not say navigation, because the plan for irradiation is already existing before the device would be used. It is basically verifying that everything is going according to plan. That actually the original model of the patient had with the location of the tumor has not changed during the therapeutic procedure lasting several weeks. Mm-hmm. And it is very often not true. So there are, of course, changes. The reason of the therapy is to cause the changes, because the reason should be to remove or to kill basically the tumor. So the changes are logical.
Here we are obviously in the medical field, but as we also say usually, the design of the futuristic device, BeamTraX, seems to be similar to the systems used in CERN by physicists who are trying to explore the fundamental structure of matter. Where are the similarities, Jan?
Actually, it is very similar arrangement to CERN experiments. For example, discovery of Higgs boson was done in similar way. So there were two beams, two particle beams, protons and protons intersecting or meeting in the middle, in the interaction point. And this interaction point is surrounded with similar types of detectors. Basically, those detectors we are using here are coming from this research in CERN. And they are recording all the particles which are created in the intersection point. Here we don't have the other beam. Instead of other beam, we have a patient head. Mm-hmm. So basically the particles which are interacting with the patient head, they would generate the same or similar secondary particles or secondary radiation. So the use of this CERN-based detector is pretty logical, because it works very similarly.
How does it feel, Maria, to bring this originally very fundamental tool to real-life application as medicine?
So for us, even seeing the whole project, we are now very happy to have it in the clinics. There were many people working on it, and we came from very small steps, and now to have a clinical device, it's amazing for us.
Unseen Talks.
Maria, what's the history of the project? Because you are working on it several years, many years, and there are many contributors as well. So who is contributing, and what's the history? How long do you work on it?
So we work on it since 17 years.
Something like that.
Yeah. And we started in a very small, like me, Jan and Carlos, trying in the beam. And now with the time, we need, of course, support of bigger institutes. So the first one is the National Center for Tumor Diseases of Germany, which actually provide the financial support of the whole project. At the German Cancer Research Center, there is the technical research focus where I work with my team. And then the HIT facility belongs to the University Hospital of Heidelberg. So there everything is taking place, and it's also covered by all the legal necessary things. So this is very important, of course. Yeah, and we work with ADVACAM, and the whole technology is coming from CERN, and we have also very good relations there and can discuss on a daily basis.
Yeah, and what was actually our role in the project?
Actually, in the beginning, we were exploring whether it is possible. So there were many experiments performed to understand what kind of radiation we can really use for this monitoring, how this radiation would be detected, how we can recognize out of many other particles which are created, which particles would carry useful information, because there are many types of particles which we cannot use, like gamma rays. They could be used, but not with our principle. Electrons, which are also not useful because they don't conserve the direction, they change the direction. So for the reconstruction of the place in the head, they are not good. And protons and heavier fragments, they are very good. And we had to understand what is the response of the detector, what it would be the optimal operation of the detector, what kind of data to be recorded, whether we can reconstruct from that data the useful information. And then after all those experiments, which were performed over many years, there was idea of the final device, and that was beginning of that project, which was already pretty advanced in advanced state of understanding, and the point was to determine optimum geometry, which was role and work of a group in Heidelberg. There were many experiments to understand what would be optimal arrangements of the detectors, and ADVACAM actually was constructing prototypes which was used and tested, then a whole system consisting of many of those modules, then implementing various software tools and triggering tools. So there are many actually small steps to create such a system. And a very last and very important point was to bring it to this clinical use, because there are many rules and regulations which we cannot actually do. That was exactly what people in Heidelberg had to do.
Sure. Back to the clinical trials at the Heidelberg University Hospital. Mária, what are the results so far? Can you really guide the beam more accurately and reduce the safety margins?
So we are at the very beginning of the study, but we have some promising results. So you can see here example how a patient is irradiated. So it's our model. So you can see here the dose, radiation dose, which is deposited really in the central region of the head. And there from the secondaries, we would like to see whether it was positioned correctly. And here you can see also this experiment on a model. So here you can observe the number of fragments which we detect with the detector. And here you can see first with this silicone, we simulated a situation where there would be swelling of the surface of the patient, of the skin. And you can see the result actually. The all orange area means that there was some change, and you can see that it's exactly in the place of the silicone.
Yeah, in fact, these pictures and other works were already published in Nature's scientific reports with some initial results. The setup was able to detect and measure a dose shift of 1.5 millimeter. What does it mean from a clinical perspective?
So that's already very promising, because the margin has the size normally in the head of 3 millimeters. But as you can see, it was shown very precisely. So we are still, we think there is space on the top, so we can move even to better accuracies and the smaller changes which can be detected.
So at the end of the day, you can shrink the safety margins. And are there any additional benefits, such as maybe enabling us to use higher doses?
Exactly. So when the margin is smaller, we can allow the same dose to the surrounding organs, which means that we can increase the dose in the tumor, which is very important, for example, to organs which are, to tumors which are not so sensitive to radiation, so radiation-resistant tumors. And there it would be a very good advancement. And then we still don't know how much we can increase the dose, so we are very curious.
How many patients have you had in the study so far?
So we have now 15 patients were in the study which were measured, and we can see what is very nice. Most of the patients, we cannot detect any changes. And we have a few patients where we detect minor changes in the regions where we would expect it. For example, on the surface of the bone, which is then neighboring to cavities, so space where it's just air. And there is expected that with very small changes like shifts of the bone, we can see the changes. But here I would like to say that it is always what we see still within the margin, and it is still safe for the patient. So we don't have any suspicions about treatments of the patients.
Yes, and anyway, it's still the proof of concept phase.
Yes.
But what's the ultimate goal?
So the ultimate goal would be that we measure during irradiation of such a patient, and in case that we spot some differences to the previous measurement or to the calculation, we could see, we could tell to the medical doctor, so we think there might be some changes, and in this case he can initiate a CT of the patient to confirm very precisely where is the change and what is the size of it.
Unseen Talks. Success stories with a bite of ADVACAM inside.
And what's the next steps we have to do?
Actually, after this clinical study, which is up to a group in Heidelberg and evaluation of its benefits, we can think about improvement of this method. This, let's say, system as it is composed now is very good, actually, but everything can be improved. So we have already some ideas how to make it better, faster, more effective, to measure other quantities, not only where the particle is going, but also what is its energy, for example, which allows us to reconstruct the interaction much better and extract more information out of the measurements. So that would be like logical evolution of upgrades, let's say, of the device.
Could the device, the BeamTraX, be replicated and implemented in other ion beam irradiation centers all over the globe?
Yeah, it can be directly transferred to other facilities which use carbon ions for treatments. So it doesn't work for proton treatments because we don't have this kind of secondary radiation for protons. But the facilities which are using the carbon ions, which are more precise, there it can be used, yes.
Actually, I have to add that, of course, the use of these carbon ions is not restricted only to head. So one can use it for other parts of the body. For the other parts of the body, probably the shape of the device would look differently. So we can think about different arrangement. This arrangement is very well adjusted or adapted to head shape. Mm-hmm. So if it would be behind of other part of the body, the arrangement would be different. So there will be probably some modifications for different types of cancers or patients.
Back to the Unseen Talks, we are talking about ion beam radiotherapy and current improvements we are working on. For patients and their families who are dealing with the brain cancer, what message of hope can you share based on the current project?
Yeah, so the message hopefully will come more in the future. So we are in a proof of concept phase. And in principle, it is so that when a patient has this type of tumor, which is fortunately very rare, can come to the HIT facility, and when he or she is irradiated, then the measurement can be performed. Mm-hmm. But at the current stage, we can not influence the treatment, meaning even if we would see something suspicious, we are not first allowed to change the treatment. But when we collect experiences and we are then very sure that the measurement is reliable, then as you said, for example, the dose could be increased, and therefore hopefully also perspective of the patient.
In how many years do you expect to happen this?
This is difficult to say. So it will be at least several years. So.
And meanwhile, I guess other clinical trials will run. Are there any opportunities for new patients to be involved in the study?
Yes, this is in principle what I said, that patient with this kind of tumor, when they are irradiated at the facility, which takes also patients from abroad, when this kind of treatment is indicated, then the patient can be included in the study.
Okay, thank you, Mária, for being here at the Unseen Talks podcast. And thank you to you, listeners, for listening to the podcast till the very end. And please stay tuned in more success stories with a bite of ADVACAM Inside.
Unseen Talks are brought to you by ADVACAM, a world-leading producer of single-photon imaging and particle tracking cameras. We're imaging the unseen.